Flight guidance.
Go.
Going to command.
Roger.
Flight, we're on internal cooling.
Under internal cooling.
S1C locks his pressure item.
November 9th, 1967. The countdown for the Apollo 4 mission was in its final seconds. This was the first flight of the massive, complex Saturn V launch vehicle, which will one day start men on their way to the moon. Atop this rocket, reaching 363 feet into the sky, sat an unmanned Apollo command module scheduled for its most severe test yet. To the over 400,000 people who worked for this day, the Saturn V, with enough power to put 85 Mercury capsules into orbit at once, and its unmanned payload, symbolized something more than the thousands of bits of data to be returned. The success of this mission would say, we're packing our suitcases, and we're heading for the moon.
Ignition detected.
Roger.
All engines go.
Liftoff auto flight.
At liftoff, control of the mission switched to the Manned Spacecraft Center, Houston.
All engines still go.
Roger.
Flight fighter, we're receiving data. Trajectory looks
Mark
normal.
25. Mark 25, Roger. GNC, how are you?
Go flight.
Ecom?
Go flight.
Booster good?
Go at this time.
Status for staging, booster?
Go flight.
Fido?
Go with all sources.
Roger.
Flight RSO green.
Roger, green.
Inboard out.
Inboard out. Tower jet. Roger, booster, it looks like...
Throughout the launch phase of the mission, Saturn V, the most complex of all American launch vehicles, performed flawlessly, a tribute to the Marshall Space Flight Center, responsible for its design and construction.
Flight, we're real good.
Roger. Guidance, how about you?
Looks good. Verify guidance. Initiate.
Booster, you got a water valve?
Fly water valve open.
Roger. Ecom, how are you?
Water boiler looks good, flight.
Roger, spacecraft. GNC, how are you?
Looks good, flight. The attitude systems agree.
Roger.
Flight to ground track is nominal.
Roger, retro. Okay, booster.
In mission control, flight controllers monitored the burn of the spacecraft's service propulsion system that took the command module to its over 11,000-mile altitude, preparatory for re-entry.
Guidance. For go flight.
This view will be seen twice by the lunar crew, once while outward bound, again on the way home. A second burn of the service propulsion system gave the spacecraft impetus for its 25,000-mile-per-hour entry into Earth's atmosphere, simulating a return from the moon. This was the most severe test yet of the heat shield, the barrier with a thickness of less than 3 inches that protects the spacecraft and crew from the 5,000-degree temperature of re-entry. The command module, after its unmanned flight, splashed down within sight of its nominal target point. Data analysis showed that it had actually entered somewhat faster than originally anticipated, and the heat shield more than stood up to this strenuous test. While the temperature on its surface exceeded 5,000 degrees Fahrenheit, the interior of the spacecraft never got above 70 degrees. One possible problem area on Apollo 4 was the vibration pattern of the Saturn V during the launch phase. A similar problem in the Gemini program with the Titan rocket had caused much concern until engineering changes had been made. At the Manned Spacecraft Center's acoustic and vibration facility, the vibration pattern of Saturn V, determined from post-flight analysis, was programmed into a computer-driven test vehicle. The object, to see if an astronaut could function properly during this stress period. The test subject, Gordon Cooper.
Actuate your left hand, go, 4.5. Okay, I didn't observe any needle movements on any of the needles.
Capcom, I was real good. We got good voice on that.
Okay.
The voice jerky, observed no needle movements.
That's fine. No needle movements, and I was able to have good vision on all of the titles within.
The results? Man can function to fly the vehicle during the vibration period. There is no problem here. While the post-flight analysis of Apollo 4 proceeded, preparations were underway for Apollo 5, the first flight test of the lunar module. This flight, set for January 1968, would check out the final space hardware necessary to complete the first manned lunar landing mission. Success for Apollo 5, hard on the heels of Apollo 4, would mean we were well on our way to the lunar mission. While the first flight lunar module awaited its mission at Cape Kennedy, engineers and ground crews at the Manned Spacecraft Center readied this lunar landing research vehicle for its multiple flights at the hands of NASA test pilots and astronauts.
All 3 units, complete and ready, light recorders up. Start your breath. You want to run at 600.
This free-flight prototype is the forerunner of the training simulator to be used to train astronauts to land on the moon. Using a jet engine for primary thrust, the vehicle is taken to a prescribed altitude. At this altitude, the jet engine is throttled back and controlled electronically in its gimbal system to support 5/6 of the vehicle's weight, simulating lunar gravity. Throughout the ascent and descent flight phases, attitude control is achieved by attitude rocket clusters. During the simulated lunar descent, the pilot flies the vehicle on descent rockets using lunar module type controls electronically governed to give accurate lunar module response characteristics. Once the simulated lunar descent is underway, the pilot flies the vehicle to a landing point marked on the runway and touches down. But while this simulator was being prepared for astronaut training, other simulators were already in use in both the general and specific mission training programs. Flight crews for the early Apollo Earth orbital missions were training in the 3 command module simulators, number 1 located at MSC Houston, numbers 2 and 3 at the Kennedy Space Center. These are static-based, computer-driven devices which simulate, through visual and audible means, the entire Apollo mission to be flown in the command module. The lunar module simulator bears the same relationship to the lunar module as the command module simulator to the command module. These simulators, too, are located in Houston and the Kennedy Space Center. While the visual window projection systems were not fully operational, the vehicle systems could be actively simulated, and flight crews as well as ground test crews were being trained. Other simulators achieving operational status at the end of 1967 included the Command Module Procedures Simulator and the Lunar Module Procedures Simulator, 2-part task trainers operated in conjunction as a single facility. The Dynamic Crew Procedures Simulator is a hydraulically powered moving base trainer which duplicates the motions of the spacecraft during liftoff, re-entry, and other powered maneuvers. Crew stations of the command module and the lunar module can be interchanged, allowing maneuvers in both spacecraft to be reproduced by a single simulator. The Translation and Docking Simulator, mounted on air bearings, features a lunar module crew station from which the astronauts practice docking with a mock-up command module for future Earth orbital and lunar missions. The Water Immersion Facility is an underwater simulation tank in which training was conducted under neutral buoyancy, simulating weightlessness. The active inclusion of these simulators in the training program for Apollo missions denoted the nearness of manned flights. While the missions were readied and the crews were trained, engineers at MSC moved toward solutions of spacecraft problems. One of the most significant series of tests was the flammability study. Original spacecraft material was tested under spacecraft pad pressures and orbital pressures. This nylon, under a pressure of 16.2 pounds per square inch absolute of pure oxygen, burned at an unacceptable rate. This duplicates pad pressure. This replacement material, called PBI, was found to be more acceptable. As was this replacement material called beta fabric. As a result of this testing, former flammable materials were replaced by new products, many of which were not available during the design and construction of the early Apollo spacecraft. And this flammability testing led to other changes within the spacecraft. For instance, electrical wiring has been rerouted, isolated, and covered with new insulators. Plumbing joints have been modified and resealed. New fireproof stowage was introduced for flammable items such as food and paper products. A unified quick opening hatch was incorporated into the design of the command module to allow quick egress on the pad. But the flammability studies produced one hard fact that would cause a major decision to be made early in 1968. The fact was simple. Under the 16.2 pounds per square inch absolute pressure of pure oxygen, nearly anything would burn. This was not true at the 6.2 psia spacecraft pressure in orbit. The decision then would be announced that on the pad, the spacecraft would use a nitrogen-oxygen atmosphere at 16.2 psia. The astronauts would breathe pure oxygen while sealed within their suits. The pad atmosphere would be vented gradually in orbit and replaced with a pure oxygen atmosphere at the lower pressure. Planning during the design of the Block 2 spacecraft had allowed for this possibility. The result? No significant delay in the program. At MSC Houston, other lunar mission support efforts reached operational status. The observatory of the Solar Particle Alert Network was in full operation, including its optical telescope, radio telescope, and data analysis facility. The MSC Observatory is in continuous operation in conjunction with the other observatories in the span chain, including similar optical and radio observatories at Carnarvon and the Canary Islands run by the Goddard Space Flight Center, and optical observatories managed by the U.S. Air Force and the Environmental Science Service Administration. In May 1967, the Carnarvon Observatory was the only observatory in position to make detailed observations of solar activity of particular interest to Dr. Van Allen, discoverer of the radiation belts surrounding Earth. Through the regular channels by which SPAN collects, analyzes, and publishes this information, in conjunction with the international scientific community, Dr. Van Allen was able to get the data he needed. This is just one small example of how, though designed primarily to support the manned lunar landing by supplying data on solar flares, the Solar Particle Alert Network provides a valuable service to science outside its primary realm. In further support of the lunar mission, the Lunar Receiving Laboratory began tuning up for its post-flight role. While many standard state-of-the-art techniques are used here, the lab is unique in the integration of the number of disciplines involved and in special handling and measurement facilities. The radiation lab, for instance, located 50 feet underground beneath the LRL, provides background radiation shielding to such a degree that it can measure low-level radiation better than 3 times lower than at any other radiation lab in the country. The shakedown, preparatory to full-scale simulations of lunar specimen handling and analysis, is underway. These are tissue cultures of common earth-grown plants raised in a germ-free environment. While it has lost its shape, this is a tobacco plant. In this form, the plant is extremely susceptible to disease and quite delicate. Tens of thousands of these cultures will be used to test the lunar samples. At the end of 1967, the people who will handle these plants were being trained. Animal handlers had to be trained. These white mice are the 4th generation of mice raised in hygienic environments and have lost all resistance to disease. The touch of a human hand with the germs it carries could kill them. Yet they must be fed and their cages cleaned without contaminating their environment. These mice, with other animals and the plant tissue cultures, will be used as life detectors. They will be placed in proximity to the lunar samples or ingest small portions with their food or by hypodermic injections. What will happen to them? The chances are nothing. Several doctors at the Lunar Receiving Lab have stated that they would be willing to subject themselves to the lunar samples in the same manner that the mice will be exposed. The probability is quite low that any life, including harmful epidemic virus or bacteria, exists on the surface of the moon. Yet, when combined with the possible risk of exposing the population of Earth to extraterrestrial living material, these precautions must be taken.
Ignition detected. Roger.
The spectacular liftoff of Apollo 4 represented the dedicated efforts of hundreds of thousands of people. Problems were faced and solved. Other problems were on their way to solution. While the manned flights are still ahead of us, during the last half of 1967, more building blocks were added to a complex structure, a structure that will one day reach to the moon.
Go with all sources. Roger. Booster good? Go at this time. Go all the way, booster.